Hello and welcome to the 8th week of this course. In the last week we covered the basic but important theorems about compactness, namely the Heine-Borel theorem, which gave the criteria for compactness of subspaces of the real line, and in fact for a linear continuum, and also the Tikhonov's theorem, which gave the statement that arbitrary Cartesian products of compact topological spaces is compact, and from there we deduce that closed and bounded subspaces of Rn are compact. Now in this week we will specialize to the case of metric spaces, and we will discuss compactness in metric spaces. In particular, we will see the generalization of two known results from calculus, which says that first one is the extreme value theorem, which said that if you have a function, continuous function from a closed interval, let's say real valued, then so it is a continuous function, then f achieves its supremum and infimum values. So by which I mean that if capital M is the supremum of the values f of x for x in the interval AB, and small m, which is the infimum of the set of values fx for x in AB, then there exists points CD in the interval AB such that f of C is equal to m and f of D is equal to capital M. So in general, if you don't have a closed interval, then it's easy to construct examples where this does not take place. So I encourage you to think about a continuous function for which this condition is not fulfilled. But when you have the closed and bounded intervals, then of course you have this extreme value theorem, which guarantees that f will achieve its supremum and infimum values. So this first statement actually holds for arbitrary generalized to arbitrary compact spaces, not just compact metric spaces. And the second result is about the uniform continuity theorem, which states that if f is a continuous function on a closed interval, then then f is uniformly continuous, and this result will be generalized to generalization to compact metric spaces. So we will replace the closed interval AB with a compact metric space, and the target will also be a metric space. So here the uniform continuity, uniformly continuous, means that if f is continuous, then the epsilon delta definition of continuity is that given epsilon greater than 0 and x in AB, so depending on these two quantities, epsilon and x, there exists a delta greater than 0 such that mod x minus y is less than delta implies mod of fx minus fy is less than epsilon. So this is the definition of continuity, and note that the crucial fact here is that delta depends on both the point x, the chosen point x, and of course the chosen quantity epsilon. So in general delta will depend on both x and epsilon. However, uniformly if the function is uniformly continuous, then there exists delta which is independent of the chosen point, independent of x, and this is what is meant by uniform over x in AB. So this is where the term uniform comes into the picture, and so we will generalize this result, which is well known from calculus, to the setting of compact metric spaces. So let us begin with the extreme value theorem. So let us look at the statement of the extreme value theorem. So we start with the compact topological space X, and we take Y to be a simply ordered set given the ordered topology. So if you consider a continuous function f from x to y, then the statement says that there exist 2 points C and D in X, such that we have f of C is less than or equal to f of X, it is less than or equal to f of D for all x belonging to X. So which means that the function achieves its supremum and infimum values. These are precisely at the points C and D, and the range of the image of the function fx is contained in the range from fc to fd in the simple order defined on Y. So of course if you take x to be AB and y to be the real line, then we get the extreme value theorem that I mentioned before from calculus. In calculus, so it is a special case of this theorem, and just as the intermediate value theorem depended only on the connectedness property of your topological space for the domain of the function, continuous function f, similarly the compactness property leads to the extreme value theorem. So let us look at a proof of this theorem. So to start the proof, we first note that the image of the function f, the image of f, so let's call it z, this is f of x, this is a compact subspace of y, because X is compact, and we have seen that images of compact sets under continuous functions are compact. So fx is compact, and what we will do is we will show that fx has a largest element m and a smallest element small m. So since z is of the form f of x, if it has a largest element, this implies that there exist c and d in x such that small m is less than or equal to f of, so m small m is equal to f of c, is less than or equal to f of x, is less than or equal to capital M, which is f of d, and this is true for all x in X. So we just have to show that this set Z has a largest element and a smallest element. So we'll just give the proof for the largest element, and the proof for the smallest element is similar. So to show that Z has a largest element, let us suppose to the contrary. So suppose that suppose that Z has no largest element. And now consider the infinite rays minus infinity to Z for a Z in capital Z. So what is this set? This is by definition the set of points in Z. So let me call it lambda. So lambda in Z such that lambda is strictly less than Z. So this is the open interval minus infinity to Z, and we consider all points lambda such that lambda is strictly less than Z. So we'll call it an infinite array. And so for each point Z in our space capital Z, we have such an open set. So this is open in the order topology, simply because it is a union of basis elements. So one can check. So I'll leave this as an exercise to check that this is indeed an open set in the order topology. So now we can have an open cover of Z using such infinite rays. So this collection UZ indexed over capital Z. So each UZ is this infinite ray minus infinity to Z, is an open cover of capital Z. And since Z is compact, there exists a finite subcover. So let's say uz1, uz2, and so on. Let's say there are n such. So finite subcover of Z of this form. And this means that Z is the union of all these finitely many infinite rays minus infinity to Zk, where k is from 1 to n. However, note that each of these Zk's belongs to Z. So we have a contradiction because there are only finitely many Zk's and there must be a largest one. So this means that there exists a largest element among the set of points Z1, Z2, Zk, Zn, sorry, and so let us say some Zm is the largest, and this means that Zm does not lie in any of the open sets Uzk for all k belonging to the set 1, 2 up to n. And this is a contradiction since Zm belongs to Z and the Uzk's cover Z. Uzk's cover Z. So this means that this implies that the Z, which is the image of X, Z has a largest element. Let's call this M, and since Z is of the form f of X, this implies that M equals f of D for some D in X. So we have shown that the image of this compact space under the continuous map has a largest element, and similarly, using a similar argument, there exists a C such that M equals FC is the smallest element of Z. So this proves the extreme value theorem. Now we move on to the uniform continuity theorem, but before we can state that, we need some preliminary notions. So the first definition is that of a distance from a set in a metric space. So now we specialize to the case of metric spaces, and so for this we suppose that XD is a metric space. So we endow X with the metric topology coming from this metric function D, and let A be any subset of X. So then we define the distance of a point, of a chosen point x0 in X to the set A as follows. So we denote this by dx comma A, this set A that we have chosen. So this is x0, dx0 comma A, and this is by definition the infimum of the distances dx0 A for all. So the infimum is taken over the set of all points in A, and so this is the distance. This is how we define the distance from a set to a point in a metric space. Now this lemma about this distance function. So this is lemma 1.2. So this lemma says that this the function f defined from X to the positive real line with the subspace topology is so defined by f of X is equal to d of X comma A. So we fixed for fixed set A. So we define this function as just the distance of X from this set A. So this function is continuous, and this follows from the triangle inequality. So we have to show, so we can, since X is a metric space, we can use the epsilon delta definition. So given epsilon greater than 0 and X in X, there exists a delta greater than 0 such that we should have that d of X comma Y is less than delta, implies that the modulus of fx minus fy is less than epsilon. So this is the epsilon delta definition, and we have seen that this is equivalent to the open set definition of continuous functions. And so we just have to translate this into our function f. So what we want to prove is that there exists delta greater than 0. So again, given epsilon greater than 0 and X in X, there exists delta greater than 0 such that dxy is less than or equal to delta, or let's say less than delta, strictly less than delta, implies that the modulus of dxa minus dya is less than epsilon. So we have to show this. So this is to show. So how do we show this? So to show this, we observe that dxa is less than or equal to dxa for all a in A, because this is the infimum of all such dxa's. So the distance of X from A must be less than or equal to dxa for any a in A. And now we can use the triangle inequality to say that this dxa is less than or equal to dxy plus dya, and this means that dxa minus dxy is less than or equal to dya for any a in A. And now take the infimum over A on the right side. So taking the infimum over A on the right hand side, we get dxa minus dxy is less than or equal to dy comma capital A. And this means that dxa minus dya is less than or equal to dxy. So just rearranging these quantities, we get this inequality. And similarly we can interchange the roles of x and y. So we have dya minus dxa is less than or equal to dxy. So taking these two things together, so 1 and 2 together gives you the required inequality that will prove the continuity of this function. So modulus of dxa minus dya is less than or equal to dxy. So choosing delta to be epsilon itself, so we get that if dxy is less than delta, which is equal to epsilon, this implies that modulus of dxa minus dya is less than epsilon. So this means that this function fx, which was dxa, is continuous. So this will come in useful for the next theorem that we want to show. And for this theorem, we introduce another concept. This is the diameter of a set. So the diameter of a set in a metric space. So let XD be a metric space and A be a subset. Then the diameter of A is defined as D. So diameter of A, we denote it like this. This is the supremum over of the values dxy, where x and y are pair of points in A. So the supremum is taken over all pairs of points, and the maximum such number is called the diameter. So note that diameter of A may not be finite. For example, if you take x to be the same as A to be the real line, then the diameter of the real line is plus infinity, because the distance between any 2 points can grow larger and larger and larger, and so there is no finite diameter for R. Now set is called bounded if, so set, let's call it A, is called bounded if the diameter of A is finite. And notice that this concept of boundedness is the same as the one we gave earlier. So this means that A is a subset of some metric ball with some center and some radius r. So for some x naught in x and r greater than 0. So you can check that the diameter is finite if and only if it can be covered by a very large Euclidean ball, a metric ball. Okay, so notice that boundedness has nothing to do with compactness. So boundedness, so this is a remark. Boundedness does not imply compactness. So even if you assume a closed subset, so even if there is a closed and bounded set, it does not imply compactness. So, and the Heine-Borel theorem worked only for the Euclidean distance function, the metric function, and in general, closed and bounded subsets of compact spaces may not be compact. So an easy example is the set of real numbers, and we can take the following metric d bar of xy. This is defined as the minimum of dxy, so the usual metric on R, x mod x minus y, and 1. And it turns out that the topology tau d bar is the same as the standard topology on R. So I want you to prove this fact as an exercise. I leave it to you. So using the basis criteria, you can prove that these two are indeed the so both the metric topologies of the usual Euclidean metric on R and this d bar metric give the same topology, which is the standard topology on R. And note that the diameter of R with respect to d bar is less than, or well, this is actually equal. This is actually equal to 1, because we have taken the minimum of any two distances and the number 1, and so we know that there are many points within R which have greater distance than than 1, so the diameter is actually equal to 1. So, and we know that R is not compact in the standard topology. So closed and bounded sets in a metric space may not be compact, and the Heine-Borel theorem is very specific to the Euclidean distance function. So with that said, in the next lecture we will introduce the concept of a Lebesgue number, and we will prove a very famous theorem called the Lebesgue number lemma, and using that Lebesgue number lemma we will prove the uniform continuity.